ओके, आवाज आ रही है क्या? हेलो। हेलो।
Yes, sir, you are audible.
ओके, so first let me ask if you have any question regarding our previous lectures on okay, so no question. So I have one question for you. What kind of materials we can get information from X-ray diffraction? I mean, depending upon the you know diffraction lines, how you can say a material is crystalline, how you can say material is amorphous, and how you can say material is a single crystal. Anyone? How you can say from XRD pattern that this material is crystalline? Means crystalline
Sir,
means
the
mhm.
crystalline materials have sharp peak and the amorphous have broad peaks.
And what about, so what do you understand by single crystal? Okay. And if you have, for example, any kind of strain in your system, then how you can get the information of strain from there? based upon your diffraction pattern. I mean, X-ray diffraction pattern. Anyone? Hmm? Yes, yes, yes. कौन बोल रहा था?
Sir, from excited diffraction, we can calculate the FWHM and we can use it for Williamson Hall plot to calculate the strain.
Yeah, no, that is okay. But question, what you need to do basically, like, okay, you have, if you have some diffraction pattern, I mean, X-ray diffraction pattern. So you have 2 theta versus intensity, like 2 theta is on x-axis and intensity is on y-axis. Okay, so intensity is what, that is basically uh, the number of scattered photon, basically, you know. So, like, first thing you have to do, what you have to do, I mean, you want to check if it is some kind of compressive strain or it is expensive expansion strain, basically, not expansion. Means, is there is expansion in the crystal lattice or there is a compression? How you can do that, basically? My question is that.
Sir, first we will check the diffraction pattern. It means how many peaks or which type peaks is observing.
Mm-hmm. I mean, which type of peak? So what you will observe, you will note down the 2 theta value. Yes.
Yes, sir.
So first thing you had to do, you had to note down 2 theta value. Okay, all the peaks. Okay, then you have to match it with the standard one. Okay, so now if you see there is a mismatch, for example, if your standard peak is at, for example, 45.3, and if you have your your observation, your experimental peak, it has 44.5, then what you can say from here? If you calculate the spacing for both 2 theta value, then what is your observation? I mean, जो आपकी d वैल्यू आएगी वो कम आएगी या ज्यादा आएगी स्टैंडर्ड से? Suppose you have 2 theta is basically 45.3 degree. Okay, and this is your experimental, for example, and then 2 theta equal to 45.0 degree, and this is your standard. Okay, no, we are not sharing any screen right now. I'm not sharing any screen. Okay, so based upon 2 theta value, how you can, because you know Bragg's law, 2d sine theta equal to n lambda. So simply you need to calculate d spacing. So you have to compare the d spacing. If d value is less, means then you are going towards lower theta value. Means lower theta value means your d spacing is more or less. It will be more. So more means expensive. So you have to do a proper analysis. So there are a lot of information you can get from. So first thing you can get, okay, about what kind of material it is, whether it is crystalline or it is amorphous. Then just hello. Yes. So we can get information about the crystallinity, amorphization. If your material is amorphous, maybe you will not see anything. Okay. Or the peaks are quite broad for this. And in case of single crystal, for example, because mostly powders are polycrystalline. Okay? Polycrystalline mean you have most of the planes you can see basically. But in single crystalline material, you will see only specific planes. Okay? And then you can calculate the crystallite size. So, and then you can get information about uh, the strain. So, in the system. So these are some basic information you can get from there. Okay, but there are many. Okay, so these are mainly main things basically that you can get. So next thing, a very important topic we are going to introduce today. We have. Uh, Let me share my screen. So I hope you can see my screen. Yes. So next thing is electron microscopy. So if you are working with materials, you will need microscope. Okay. And mostly you heard about optical microscope. Okay. So what is the working of optical microscope? It is same as working of electron microscope. Okay. Only the difference is you have uh, light there, but here you are dealing with electron beam. Okay. So let us start with first because uh, if you know the cost, then you have to think twice before asking for electron microscope facility. Okay, so it is not so common. So typically, if we talk about commercial TM, transmission electron microscope, where your electron they are basic passing from your sample. Okay, so your sample should be electron transparent, means they should be very thin. Okay, so commercial transmission electron microscope cost about $5 for each electron volt of energy in the beam. So if we add on all the available options, because it's not only you have you need to accelerate electron, but you have optical system, you have electromagnetic lens, then you have detection system. So roughly it will cost around $10 per electron volt. And if you see any commercial microscope, then the energy is basically from 100 kilo electron volt to 400 electron volt. Sorry, 400 kilo electron volt. Okay, so you can estimate this. You just multiply it. Okay, so it is very one of the expensive instruments, and mostly you need very solid reason to have electron microscope in your place. Okay, so in this class we will try, I mean, just talk about some story about electron microscope, and then next class is, because it's completely a very big topic, because it is not just giving you information, I mean, or pictures, because it is just not a camera, but it gives you complete information today. If you have some modern mm, electron microscope, I mean, you can do spectroscopy, you can do optical, you can do even magnetic, most of the things you can do on a electron microscope. Okay, so and those who are working with nanotechnology, it's very important for them. Okay, so what material should we study in transmission electron microscope? So we can examine some kind of metals, alloy. If you are mixing more than two material, and if you want to find where is the first material, where is the second material, and how they you know connect each other, for example, so you can do that also. And then some kind of ceramics, glasses, polymer also, semiconductor, and other composite material. Okay, but only one thing is, if I see uh, the sample preparation, you need some kind of specific sample to do this. Like, it is not like you have something and you are going to put in electron microscope, because you are going to deal with electrons. So electrons should pass through your material. If your material is thick enough, then you will not get anything there. Okay, so in addition to thinning them from bulk state, particle and fiber of some of these materials are also commonly studied in such shapes. They are sometimes thin enough for direct you know, transmission electron examination. And when we are talking about nanotechnology, I mean ability to understand and control the matter at dimension from 1 to 100 nanometer, where you have unique physical properties, some are, which is very important for novel application. Okay, so we can study any kind of nanomaterial. Okay, whatever it is, powder, any thin film, but thin film it is more complicated. We will see. So today about lot one-dimensional material, two-dimension, three-dimension, or zero-dimension also. Okay, so you can get some an idea about their how is their size, how is their shape, what is their spectroscopy information, spectroscopic information. If you have, for example, three or four material combined together, you can get some information. For example, if you have low Z number, for example, any kind of oxide, or if you have, for example, gold. So in electron microscope, you can see clearly distinguish between low Z material and high Z material, because those which having high Z material, it have different electron density. Okay, so when electron pass through them, it behave differently. So it will appear dark as compared to the low jet material. And also today we have uh, uh, this cryo-electron microscopy also, where you can mostly electron microscope are operated at room temperature, I mean, but for biological sample you can go down. Liquid nitrogen temperature is very common. Okay, so we call it as a cryo-electron microscopy. This is, if you know, how we can distinguish between different kind of nanomaterial, because we are going to talk electron microscopy in terms of nanoscale material. In this slide, you can see how we can define, for example, one-dimensional material. So I said that material whose characteristics length is between 1 to 100 nanometer is basically, you call them as a nanomaterial. Okay, where you have different physical properties which are not absorbed in the bulk material. Okay, so if we talk about one dimension, so here in case of one dimension material, two dimensions are basically in nanoscale between 1 to 100 nanometer, whereas third dimension is in macro scale. Okay, so we call them as a one dimension material. And if you have one dimension between 1 to 100 nanometer and two dimensions in macro scale, okay, then you call basically them two dimension material. And where we have no dimension at the nanoscale region, we call them as a three dimension. And where you have all dimension in nanoscale region, then we call zero dimension. Basically, mostly nanopowders are in this category. So you can see from this slide here, example. So this is basically, in this picture you can see the first electron microscope that was built in 1930 basically. So why use electrons basically? So you are familiar with this optical microscope very well. You know about this, how it works basically. The same, the working is same, but now people are using here electrons. Okay, so why should we use an electron microscope? If we go in history, so TM were developed because the limited image resolution in light microscope, which is imposed by the wavelength of basically the visible light, which is from 400 to 700 nanometer. So only after electron microscope was developed, because how you're playing with the wavelength of electron, the electron wavelength. So when you accelerate them with very high energy, then basically if you calculate the wavelength, your wavelength, so you have some relativistic effect. So the wavelength is in picometer. So means that wavelength is related with the resolution. So you can you can see basically at atomic level. Okay. So how the history, develop, so about de Broglie, you know, theory of electron that have wave-like characteristics with a wavelength which is less than the visible light. Okay, so if you see this experiment that two different scientific group has done, that is, one is Davison and another was Thomson. They did, electron diffraction experiment first time to to tell about the wave nature of electron. And after that, the idea was developed by uh, a scientist named Ruska. So they are basically and Knoll. They are working here for this first electron microscope. So it was 1930 basically. So, but the regulation is very important. Uh, suppose if someone asks what is microscope, so basically we call that to magnify small images into big images, which we cannot see by naked eye, basically. Okay. And if we talk about resolving power of our eyes, so it is between zero point 0.1 to zero point 0.2 millimeter. So it depends basically on your eye, how it is basically. It is good or bad, basically. Okay. And but if you want to go finer, for example, below zero point 0.1 millimeter, then you need basically microscope because we cannot distinguish below that. Okay. So the major development during this transmission electron microscope was due to what wavelength of electron that are smaller than so the electron that basically smaller than the atom basically. Okay. So if you see this relation is very well known. Uh, so if you see this is if you see this highlighted in yellow color, the idea of being able to see with electrons may be confusing to you. Like I have taken this quote from somewhere. So our eyes are not sensitive to electrons. If a beam of high energy electron was aimed into our eye, you would likely to be blinded as the electron kill your retina cells. But you would not see anything ever again. So an integral part of any electron microscope is basically the viewing screen where you can see uh, the electrons basically. So that is basically display. Okay. So which display the electron intensity as light intensity. Okay. So basically what happened, like you have uh, filament, you have electron gun, which produce electron beam, and then you need to accelerate those electrons, and that is basic stream of electrons. So you have to confine them and you have to accelerate them towards your sample. Then you have some arrangement of like optical microscope, you have optical lenses, but here you have electromagnetic lenses because electron is negatively charged particle. Okay. So you have electromagnetic lenses, so that is different kind of arrangement, optical system is there. And then finally you have sample, and then your electron passes through your sample, and then they come to another side, and then that electron fall on, transmitted electron falls on a viewing screen, which is a photographic plate, something like that. Okay. We show fluorescent signal basically, that is photographic plate simply. And if you see the resolution, this is given by this relation, to which we see 0.61 lambda upon mu sine beta. So here lambda is nothing but the wavelength of your electron, and this mu is the refractive index of the viewing medium, that is photographic plate, and beta is the semi-angle of collection of magnets. So that is some angle we will discuss when we will see the schematic diagram basically. So if we see, if we calculate, for example, if this uh, denominator term mu sine beta. We call this, later we will see, we call this as a numerical aperture, okay, and which is generally taken as unity 1 basically, okay, and this the resolution is equal to, basically if you see, this is half of the wavelength, so this is 0.61 lambda basically, okay. And if you calculate, for example, for as an example, for green light, uh, the wavelength is 550 nanometer, and if you know calculate the resolution, it is about to 300 nanometers. So means, like with this, you can see size of in this range basically, okay. And in TM, we can approximate the best resolution using an expression similar to this relation, which is simply given by resolution equal to 1.22 lambda upon beta, okay. So for example, if you know the wavelength of electrons, so you need to, for example, if you have 100 kilo electron volt, electron microscope which can accelerate electron to such high energy, you can simply calculate lambda and you can calculate the resolution. We will see it later. So this is the final relation basically, where lambda is connected with the energy. So in this equation, E is nothing but it is uh, energy in electron volt, lambda is the wavelength. So if we calculate this for 100 kilo electron volt, transmission electron microscope, for example, or electron having this energy, 100 kilo electron volt, if you calculate the wavelength, it is coming to be around 4 picometer. Means you can see 4 picometer inside your sample. The resolution is this basically. So this is 0.004 nanometer. So means you can see clearly, uh, you can see resolution with size which is smaller than the diameter of the atom. So this is basically 100 kilo electron volt. But this is the theoretical basically. So it is not always that you have very confined beam. There are many factors which finally calculate the resolution basically. Okay. So there are other things many, because electromagnetic lenses, there is some uh, uh, like error in that. Uh, so we have aberration, all these things. So, but this is a theoretical, for this 100 electron volt electron, the wavelength is coming to be 4 picometers. So that is basically related with the resolution. So you can go this scale with this with these electrons. So this, if you see how, if you want to understand it completely, I said in the beginning that you need, it is not only electron microscope is used for imaging purpose to take pictures of something inside your sample, but there are, it can do many other things. They can do any spectroscopy experiment. Then you can have magnetic or whatever. So it is very important to understand, I mean, how they interact with matter. So how electron interact with matter. So you can see here, and these different signal are basically are collected, and detector collect them, and they have some particular information about the sample, for example. So electron are one type of, you can say, again, they are ionizing radiation having charge basically. So which has capacity to remove the tightly bound electron or inner core electron basically. Okay. When you do this, there are different signal basically. So if you see here, this is the incident beam, and this is basically, you can say these are some kind of your sample here in yellow color, for example. And then you have different signals generated. You have secondary electrons, you have characteristics X-ray, then you have some fluorescent signal, which is in the visible light visible light regime. Then you have backscattered, means all electrons, they are not basically transmit. So you have backscattered electrons. Then you have quasi electrons, and then you have also this is the direction of the direct beam. Then you have uh, elastically scattered electrons and inelastically scattered electrons. And this signal basically, uh, this is not like if you like, I mean, the location, the physical direction of the signal is not like that. It is just for remembrance, the different signal generated. Right? It's not like backside you have only secondary electron. So it is not the case basically. Okay. So direction shown for each signal do not always represent the physical direction of the signal, but it indicate in a relative way. Okay. So you have, for example, if you have secondary electrons, for example, if you want to record EDX spectrum, we will see it later, like which can tell you about the composition of your material. So it's not like that you will use scattered electron for that. Different signal had different kind of information uh, to tell about your sample. Okay. OZ electrons have different information, backscatter has different information. Only thing you had to collect those signal, and you have to put a detector there. And yeah, then you have to optimize your signal, and that will give you particular information about your sample. I'm just taking an example here. This is uh, some spectrum where you have energy versus you know electron signal basically, that is detected uh, by your detector. Okay, so this example is based on some nickel based super alloy, some kind of super alloy made up of nickel. So you can see here, like this is energy from 0 to 10 electron volt. Okay, and if you see here, so you have to see, this is done by using these secondary electrons basically. Okay, and you can see here, you can see, for example, nickel based superalloy. So you have nickel uh, L as information. Then you have aluminum, it is the superalloy, so it has aluminum also, for example. So here you can see at 5 kilo electron volt, you will see some information about chromium K alpha. Okay, so you should know, like when you get K
Sir,
alpha
your
information,
slides, they are not changing.
slide is not changing. Where it is stuck, which side?
Sir, it's on the
Interaction.
first slide itself.
No, just a minute. Yes, now it's fine or no? Is
Yes,
it
sir, now
fine?
it's fine. Yes, sir.
Okay, let me just give you some, but we just changing slowly. Okay, okay. We were discussing here actually. This is uh, a typical X-ray spectrum where you have, you know, uh, X-ray energy on X-axis, and this is scattered X-ray. Okay, so you have to see here how X-rays are produced basically. So you have, for example, characteristics X-ray here. Okay. So when you utilize these characteristics X-ray, you will get some information about the phase composition, the composition of your sample. For example, you have three elements, for example, A, B, C, but you don't know how much is the percentage of A, how much the percentage of B, how much the percentage of C. Okay, but total it is 100%. So maybe it is A 30, B 50, C 20. Okay, but if you want to exactly know how much, then you need characteristics X-ray for this. Okay, and this is possible only in transmission electron microscope because you have electron beam and it is passing through your sample, and then different signals are generated. So it's not like all signals are used to construct the image only. So microscope is not only for imaging, it is for spectroscopy or other things also. Okay. So here you can see here from this, for example, if you see this slide here, so if you want to say how much chromium with respect to nickel, so if you calculate the area of this peak, you can get some information from here. Okay. And if you see here B and C, so this is, I'm just talking about here, the image C. So C is done, you have three different elements, and here different color is assigned to each element. So you can see here, you have majority of iron basically. Okay, so these kind of information, so composition, you can get information about composition from uh, from this transmission composition analysis from transmission electron microscopy. So just a minute. Okay, I will, because this is just a brief introduction basically, because we cannot discuss everything, but then next class we will see each part. Okay, so but there are some limitations. Okay, so first thing is sampling. Like it is not because you need very solid reason why you want to see inside your sample. You need solid reason to provide to the lab manager why you want to do this experiment. You need some solid reason because you know the price. Okay, so it is not important that if you're working with nanoparticles, for example, or if you're working with some uh, material, that you need microscope facility and you need to do imaging. So first of all, the price to pay for any hydrogen imaging is that you only look at small part of it. Second thing is you need solid reason, and uh, you in electron microscope you always see a very small portion of your sample. For example, if you see here, the scale is 100 nanometer, for example. So there are many such portions in your sample. Okay, but you are looking only small part, very minute part of your sample. Okay, so this is sampling is one limitation. You cannot see the whole sample. If you want to see a whole sample, it's very difficult. Okay, so we assume okay, your other part of your sample is all okay. Then interpretation of the images. So basically, if you see uh, electron microscope, especially transmission electron microscope, it gives you only two-dimensional images. Okay, so that is one problem basically. Okay, so for three dimensions, you need to go more sophisticated instrumentation, that is tomography, for example. Okay, and electron beam damage and safety. So that is also very important when you are going to check your sample in electron microscope, because you are dealing with very high energy, which is from 100 kilo electron volt to 300 kilo electron volt or 400 kilo electron volt. So if you see in this slide, these are same sample, and this uh, this show beam damage. So you can see the left side how the particles look like. Okay, and then here this another side you can see when you put beam for longer time in your sample. Okay, then you can see how they damage. So there is sample damage. So, but for a material scientist, for example, who are working with some kind of nanoparticles, there is not so much issue. But who are working with biological sample, working with cells or other things, then it can damage those things. So you have to very specific. I mean, in energy. I mean, how much current you need to apply, how much acceleration. Like it's not like if electron microscope can go 100 electron volt, you need to acquire images only at 100 electron volt. Okay, if 30 kilo electron volt is sufficient for you, that is fine. So damage is also there, so we have to take care for this. And most important thing in microscope is the sample preparation. As I said before, it is not like that. You cannot measure anything. You need uh, some specific sample preparation, and it is very time consuming. I will show you later what kind of sample holder we will have for this purpose. So your specimen in your sample have thin if you are going to get an information using transmitted electrons in the TM machine. So this is a relative term basically. So like anything which is electron transparent. So it depends upon sample to sample. Okay, means your electron should pass through your sample. If they don't pass, then it will not give you any information. Okay, because in next class maybe we will discuss about scanning electron microscope, where electrons is not passing through your sample, but it is just scanning the surface of your sample. Okay, so in that case you can get another thing, but in case of electron microscope, it should be electron transparent. It should pass through your material. For a specimen to be transparent to electron, it must be thin enough to transmit sufficient electron such that enough intensity fall on the screen. For example, if you want to measure thin films, so you know that thin films are on some supported substrate. Okay, so it is not like that you can directly put the thin films in uh, in microscope because the sample holder is different basically. Okay, so you need to cut your thin film and you have to make it very thin so that electron can pass through this. And this is not only a few hour job, but it will take 2 or 3 days. Sometimes you know damage your sample and you will not get nothing basically. So, but powder sample I can say it is more easy to do in electron microscope. So if we talk about some this specimen preparation, simply 100 electron volt. If we talk about specimen aluminum alloys up to, I mean, 1 millimeter would be thin. I mean, for this. So while steel would be unique, maybe hundreds of nanometers. So question is like mostly the sample should be less than 100 nanometer thick. Thickness should be less than 100 nanometer. In some cases, 50 nanometer or less. But when you go more down, it is more difficult. Okay, these are some different kind of electron microscope you can see here. So if you see in slide in the slide A, this is 1.25 mega electron volt. So this is huge machine, but 100 to 300 kilo even 400 kilo electron volt is not common basically. Okay, so like 100 kilo electron volt, mostly people from biological background, they use this. For materials, it also work, for example, but mostly you have 200 kilo electron volt. Okay, so these are different microscopes. So at the top you have electron gun, and then you have basically, if you see here in E, so this is basically electron gun which produce electrons basically, and then you have some kind of to accelerate these, to have to arrangement to accelerate these electrons towards sample. Then you have objective lens, that is basically electromagnetic lens. Okay, and then this is whole arrangement basically. You need one full big room to do this, to put this electron microscope there. And if I see here in F, for example, this is here you can see basically, if you see where I'm moving my cursor, you can see clearly the electrons basically. Okay, because you have photographic plate here. Okay, so you can see the electrons when you are doing the experiment. You can really see the electron beam here. Okay, so you can see the electron density here. So these are different modern equipment which is basically available today for imaging, spectroscopy, magnetic experiment also, and optical experiment also. So this is very important, the last slide for today's lecture. Okay, so uh, if we talk about the wavelength, okay, so I think this relation is very common. So here you can see the wavelength is given by this relation. It is basically this is the momentum, and this is basically the Planck's constant. And in TM, we impart basically momentum to the electron by accelerating them through a potential drop, which is from 100 kilovolt to 400 kilovolt or more. Okay, and to give it enough kinetic energy, so that this potential energy must be equal to kinetic energy. So this relation is well-known relation, basically EV equal to half mv square, where m naught is the electron mass. So if we use this momentum, so this is basically 2m naught under root of this 2m naught ev. So lambda, the wavelength, is coming to this. So this is basically, if you see, this relation is basically when electron is basically without considering the relativistic effect. But now the energy is very high basically, so we have to consider relativistic effect. Then this equation modifies as this, because and it is observed that below 100 kilo electron volt relativistic effects are not so much problematic, but when you go above 100 kilo electron volt, the velocity of electrons become greater than the half of the velocity of the light. So the final relation to calculate the wavelength of electron in a transmission electron microscope is this. So if you know the accelerating voltage, the charge, mass, electron, or all these things, you can calculate simply the wavelength. And then this wavelength is related with the resolution of the modern uh, electron microscope. If you have any question, then you can tell me. Otherwise, we will go for next class for this, for more idea about how it works and how the different parts of electron microscopy, some instrumentation and the principle. So, no question. Okay, then maybe. Okay. So next, see you on next day. Say yes.